Hey friends, yet another video from Ben. This is for the vector calculus class, and what we're taking a look at is quadric surfaces. Not quadratic surfaces, but quadric surfaces. Just that's the term they use. Okay. So in general, what those mean, or what that terminology means, is that you have quadratic functions of x and y and z appearing in your equation. Nothing higher, of course, than second degree. But in particular, we're not going to look at things with mixed terms in them. If you have x times y in something, it will take and twist things around and just change your axes slightly. We could certainly look at something like that. As a matter of fact, if you're looking for a project for the end of term, that would actually be kind of a neat thing to play around with, especially with all of the utilities that you've got to do graphing and stuff. Side note on that, I just discovered today how to do animations on the CalcPlot 3D. So look for those to come soon. Yeah. But anyway, what we're going to take a look at is how these quadric surfaces come about. As I'm saying that, I'm realizing that I should point you to the pages in your textbook where that is appearing at. So give me just a second to look that up real quick here. And it should be in the vector geometry chapter, so chapter 12, section 12.6, a survey of quadric surfaces. In my copy, it's page 670. If you have a slightly different copy, like an older or newer edition, or one that's not transcendental functions first or something, the page will be slightly different. But look for section 12.6 or the title, A Survey of Quadric Surfaces. Okay. And with regard to those, if you take a look at just the basic sketches, it gives you an idea of what these things will look like. Oh, nice, nice. Page 675 gives you a summary of a whole bunch of them all together. But we're going to take a look at them with the notion in mind that we're trying to parameterize the graphs. And in doing that, we kind of have to understand how the parameterizations work. So I'm trying something different with sharing screen with you. Cross your fingers. I hope that it's going to work out. So let's take a look here. And I am assuming that that did not put the Zoom window in there. I better not assume that. Let me try sharing again. All right, so that should be showing you something here. I'm writing on my iPad, broadcasting it to a web browser, and then showing the web browser to y'all. That is overkill, it feels like, but it gets done what I need to get done. So looking here, we've got x squared plus y squared plus z squared equals 1, and the graph is going to be a sphere with a radius of 1, but it's going to be an example of something where we've got an ellipsoid. So in graphing, or in parameterizing something that is an ellipsoid, we're going to try to look at those things in a way that will be more or less organized, right? And this maybe even explains to you, well, hopefully explains to y'all where the spherical coordinates setup comes from, right? So if you take a look at what we've got here, this x squared plus y squared plus z squared equals 1, if you make the conversion into cylindrical coordinates and have r squared plus z squared, then that r squared plus z squared looks, or having equal to 1, looks like a circle, right? That looks like the equation of a circle. but the circle in question lives in the RZ plane, not the XY plane. So for this thing that lives in the RZ plane, and you get a circle out of it, then you have to think that theta is allowed to be anything you want. If a variable does not appear in an equation, you have to allow it to take on any value. In particular, anything from 0 to 2 pi, you're going to take a circle and rotate it around. And so your rotated circle is going to describe a sphere. So if we're parameterizing a circle, we can always do it by either r equals cosine theta, z equals sine theta, or vice versa. Now, you should be super curious as to why I reverse those from what you normally see. The thing is, we're going to use this range from 0 to pi here for our sines. And because we let sine go from 0 to pi, let u go from 0 to pi, the sines will go from 0 to 1, while the cosine is going from minus 1 to 1. So that's why we've got a positive r value, and our z value is going to be both positive and negative. So that kind of explains what's going on with the 0 to pi range and this reverse thing going on here, okay? If you wanted to reverse these two, you could certainly do that, and instead of 0 to pi, talk about minus pi over 2 to pi over 2. Something Don said last semester suggests to me that that's probably what physicists do with their spherical coordinates. So, but this is just the traditional thing that we tend to do in the math course. Once you have the sign for your r, then you just take the r cosine theta, but we'll call it v because we're going to look at things on the Calc plot 3D in a second, and using u and v is kind of convenient there. Okay, so if we go ahead and look at that with the Calc plot 3D, and I'm implicitly assuming that the window changed there for y'all, then our plot, let's see, hopefully you can see the portion of the window there where we're setting things up. Of just setting the x and the y and the z to what we just figured out. I'm going to let my u go from 0 to 2 pi. The u, I have them reversed. Okay. So I should, in my page that I was showing you, I should have gone in there and made it say sine v instead of sine u. Okay. Anyway, though, that then is our explanation why this sort of thing works out here. Now, if you had your x squared turn out to instead be x over 2 the quantity squared, then you could have made the change in here to have set x over 2 equal to this, which means you would have 2 times that in your solution, and then you would stretch it out in the x direction. Or alternately, if it had say 9 x squared plus 9y squared and plus 4z squared, I think those were examples that we had, we could put a 3 and a 2 in here, and it would squish things in I'm sorry, it was I was supposed to divide instead of multiply. My bad. So divide 3, divide 2, and then it will squish them in the y direction and the z direction, whereas it left it alone in the x direction. Okay. Similarly, if you want to move the center somewhere, you could have 2 plus appear in there, and a minus 3 plus, I'll just leave the z where it is, and it would just move the center somewhere else. Okay, so for our parameterization of elliptical sorts of things, the key is to put it into the standard form, which is to say quantity that's like x squared, a quantity that's like y squared, a quantity that's like z squared is equal to 1. And then to use some form of this parameterization to take the things that are being squared and set them equal to. Reminder, how do you spot that you've got an ellipsoid? When you put it into standard form, you have a 1 over there on the right-hand side, and all the stuff with x and y and z is all being squared and multiplied by a positive number. Okay? All right. Then let's take a look at the hyperboloid of one sheet. So here, I feel like we've done the minimal sort of changing of the equation for the ellipsoid. We have changed one of the pluses to a minus, all right? So if you got that going on, that tells you that you've got a hyperboloid of one sheet with one minus sign. And then if you convert the x squared plus y squared into the r squared, you get r squared minus z squared, which hopefully from an Algebra 2 class, or ultimately from a Calc 2 class, it depends on when you had it, you would hopefully recognize that that looks kind of like the equation of an ellipse. Hyperbola, okay? And so we would talk about here that the equation, the identity for hyperbolic sine and cosine is cosh squared minus sinh squared is equal to 1. And that tells us that we're going to let our r, which is in the position of the cosh, be cosh, and the z be sinh, okay? And then if you think about that drawing being something like this, notice I've just brought up the drawing of x squared minus y squared equals a, and I've got the a be 1, okay? Then that being in the r theta plane and the theta changing, you rotate it around, and the sort of shape that you get out of it is going to be one of these things, okay? So your hyperboloid of one sheet. Now, if on the other hand the minus had been on the y instead, then you could easily enough change that around and just have swapped those and then had the y-axis be the axis of symmetry for this, all right? Okay, so in any case, once you have the r being the cosh and the z being the sinh, and I should make a point about that in a second, then you can substitute that r into the x being r cosine theta and y being r sine theta. I've used t and s here. If you want to use some other variable, it's fine. Now, a quick point. On the previous one here, I talked about why we chose the sine on our r as opposed to the cosine, and using that range there for your u variable. For this one, then, you could also think about, if you knew what the drawing was going to look like, that cosh only gives you positive values. If you look at a graph of it, it's roughly like a paraboloid. It's just that it goes up much faster than parabolas do. And then your sinh looks kind of like a cubic function, and so it goes to minus infinity and plus infinity. So that suggests, because we want this to go up and down forever on our graph, that we would choose the z to be sinh, okay? So we might reach this, instead of looking at the equations, we might reach this parameterization by knowing something about how the graph is going to turn out. So, all right, here is a switch in that. If we have minus x squared minus y squared plus z squared equals 1, there's two minuses there, and that's our mnemonic to tell us that we're going to have a hyperboloid of two sheets, okay? And so if you had instead had x squared plus y squared minus z squared equals -1, then in putting it into standard form, you would divide by the negative and get the two minuses over there. So any way you go at it, all right? And so the thing for us to spot is that our minus r squared, our minus part, is going to go with the sinh, okay? And then we'll have things fitting that that identity we had for hyperbolic sine and cosine. And then we go in and have our sinh cosine u and our sinh sine u. And the one difficulty we have is that our z is going to be positive or negative, but we could see that we had a z squared here. It was legal for it to be negative. So we're actually going to have to do two plots to get this drawn. Another thing to consider here is our sinh. Oh, and I made a mistake on this. Our sinh is could be positive or negative according to the sign of t. I should have just made that 0 to 1, not -1 to 1. Can I edit on this one? Nope, I can't. So I'm going to just have to cross that out and put a 0. I mentioned to y'all that I was trying something different and couldn't edit it on the fly because of that. All right, so jumping across to the Calc plot 3D, we're going to bring these two pieces up here, and you may be able to see off to the side there that I had to have two pieces in order to do that. Okay. So again, if the plus was with the y squared instead of the z squared, then you could have gone into this and what could you have done? Sorry. Yeah. If the plus had been with the y or the x instead of the z, then you would have treated the other two variables as getting your sinh u cosine v and your sinh u sine v, and then whichever one had the plus would end up with the plus or minus cosh. All right. So coming back across here, the next thing to look at is what if we had our x squared plus y squared minus z squared equal to 0. In that case, you can't put it into the standard form for one of the hyperboloids because there's no way to divide out that 0. If that had said x squared plus y squared minus z squared equals 15, sure, divide by 15. Voila, everything is in the standard form. It'll be a little bit of a headache solving for the x and y and z, but not that bad, you know. When it's got a 0, though, you can't divide by 0. When you do, it screws everything up. So what we have to look at on this is going to be that we have r squared minus z squared equal to 0. Okay. If you think back to that graph I had here, and we looked at x squared plus y, x squared minus y squared equals 0, and saw it was two intersecting lines, that is essentially what we have here. That we'll have it as z equals plus or minus r. Now, there's a trick that I'm going to pull with this. So see how I've said z is plus or minus r? So just like graphing the hyperboloid of two sheets, that you would have to graph two pieces. Well, turns out that this is a little bit slick here. Instead of having plus or minus r here, you can just let your r go, instead of 0 to 1, let it go -1 to 1, and then you get both your pluses and your minuses. Okay. So with regard to this, we can just let x and y be the r cosine theta, r sine theta, and solve and get the z being r. And because we do -1 to 1, then we'll get the bottom cone and the top cone plotted. Now, one thing to realize is that for positive r values, you're going to traverse your circle clockwise or counterclockwise as viewed from above. But once you get the negative r value in there, it's actually going to flip things around. And as thetas increase, you'll go in a negative direction instead of a positive direction, which is kind of confusing. Anyway, we will put our cone in here. I'll take out the other two pieces. So let me go ahead and take out the negatives, and you can see that if you have just positive values for u, that you would get the top cone only, but when you get both positive and negative, you get the top and the bottom. Okay. All right. Then we're going to look at this notion here of drawing a paraboloid. Right now, bear in mind, like with all the others, there's kind of a standard form to put things in. You've got, in this case, I've written z equals x squared plus y squared. You could just as easily have had y equals x squared plus z squared or something else. But we need one that's not squared and the other two being squared. And you might have to go ahead and complete the square or something so that everything fits together nicely. But then this x squared plus y squared suggests the idea of r cosine theta for x and r sine theta for y. And then you can solve for your z and get the r squared there. Please note, I'm here only going to have my r going from 0 to 1. It would not mess up anything to have it go from -1 to 1. But as someone pointed out the other day, if you've got a larger range for one of your parameters and the same number of steps, then you'll have a larger step size and you'll just get a chunkier plot is all. Okay. So let's and you might take a note here off to the side how similar the cone and the paraboloid look in the parameterizations, right? And so I went ahead here and let my u, because I've got x is u cosine theta, y is u cosine v, sorry, and y is u sine v, and my z is u squared. I let my u go 0 to 1.4 because if I only let it go to 1, it kind of looks a little bit too squat. And if I let it go up to 2, it ends up going out of the picture. So I played around with it, and 1.41 is pretty close to the square root of 2. So having the square of u up here and there suggests why you would do that. All right. So then we'll take a look here at what's referred to as a hyperbolic paraboloid. I try like heck to draw these by hand, and every time it looks a little goofy. So bear with me a bit on that. Because it's got x squared minus y squared appearing, it makes sense that you should probably be saying x is cos u and y is sin u, and then maybe give it a coefficient like v, and then you would end up with your z being v squared, but then your z's only give you something positive. And so I played around with this for a bit, and I've done this in the past. I always get a little confused about how to make these look the nicest we could manage. So, but turns out if you just say to heck with it and let your x be u and your y be v, and let your u and v go from -1 to 1, your graph looks okay there, you know. Somebody else did it a little bit differently. I did one a little bit differently of using u cosine v and u sine v, and then ending up with u squared cosine v squared minus sine v squared. And let's see, the v should probably go minus pi to pi on that. By the way, once again, it doesn't really matter whether you use 0 to 2 pi or minus pi to pi. So I don't like how that looks. I'm going to smooth it out a little bit by changing the number of steps up to 40. See how now it looks sort of like a Pringles chip, right? So, and is there a way to reset that? Because I don't like how it ended up all tilted and stuff. Oh well. Oh well. All right. So we'll jump back here. And again, just parameterizing like that probably makes the most sense. If you had to do a section of the hyperbolic paraboloid that was inside of a cylinder, like x squared plus y squared equals 1, then it would totally make more sense to let your x be the u cosine v and the u sine v. Okay. All right. Then last one of these, let's talk a little bit about those cylinders. So if you've got something like x squared plus y squared equals 1, and you're dealing with stuff where you know you're living in 3 dimensions, z did not appear in there. So z could be anything it wants to be. If the variable does not appear in the equation, it is not set. It is not restricted. So lots of times people have this mistaken impression, well, if it doesn't appear, it must be 0. Nope, it could be anything. So in order to do this plot, I'll do x and y to be cosine u sine u, because of the fact that we want x squared plus y squared to be 1. And then set z to be the other variable, v. If you're saying, why don't I just let z be z? Sure, z can be z. It's free to do whatever it wants to. But I chose it to be v just because I'm going to go to Calc 3D that uses u and v. So if I do that, then I get this plot like so. You know, we are plotting some kind of a cylinder. And then we can more generally say this terminology piece, anytime you talk about a surface that appears that does not involve one of the variables, then you can refer to what you have as a quote unquote cylinder. It's just not a round cylinder in this case. We might come down, pointing with the wrong device, sorry. We might come down here and say z equals sine x, and it doesn't involve y. And so your x is going to be a variable, and it's going to determine the z, and then the y can be the other variable. So if I take that up here, you can see that I've got this kind of a wave that repeats on and on. And then you can play a little bit with your graph about making the u be different values to make a narrower section of wave there, or even make it wider if you want to, right? But in any case, you have something from that we happen to refer to as a cylinder. It's just not a round cylinder. All right, so this has been a brief video about quadric surfaces, and hopefully that gives you a little bit of information there. And then, as I mentioned before, let's see if I can display this the other way. Your textbook, guess I should turn that up right. Right. Your textbook here on page 675 deals with this kind of stuff in section 12.6. And they go ahead and make mention that you can replace the X and Y and Z with like X over A and Y over B and Z over C and stuff like that. But they don't actually do the stuff with completing the square and transferring the center to different places. You might also notice up here at the top of the page, they do some things with parabolic, hyperbolic, and elliptical cylinders. Oh, and right circular cylinder. So those are available in your textbook and are probably one of your better resources to look at there. So anyway, yay. I just realized this doesn't really attach very well to an actual class session. Maybe I need to edit that. I don't know. All right, see you in class.